So, what we talk about when we talk about evolutionary computation? Well, I hope you like the title because it's probably the best part of this presentation. And the reason is that the title is not mine. I copied from a book. What we talk about when we talk about love, a remarkable collection of short stories by Raymond Carr. Anyway, there is evolution in the title, so I can't help talking about the second voyage of the Beagle. This ship, both Darwin around the globe between 1831 and 1836, and it allows the young Robert Darwin Charles Darwin to take observation and notice all around the globe. Now it's interesting to notice that Darwin was not appointed of any scientific role inside the Beagle, but he just went on this trip as a friend, companion friend, to keep company of the captain, Mr. Fitzroy, and his parents paid for such a long and expensive vacation, basically because Darwin was such a lazy and poor student. And this story is very interesting and definitely not have the time to talk about it. So, 1831, 1836, Darwin just collected things and notice and information of observation, and then he started thinking about it, trying to find a single simple theory able to explain everything. And he just think, keep on thinking again till for 25 years. And in 1859, he had to rush to publish something. Well, why Darwin had to rush to publish, and why the theory of evolution is usually credited both by Darwin and Wallace. It's another interesting story, and we are again not going to that. But what is interesting is that in 1859 we have this quite remarkable book, The Origin of Species, and well, the full title is slightly more wordy, and this is considered a milestone in the theory of evolution. Now, the book has been published in 1859, but it is also 1 year but appear in our logo, Politecnico. Now, my boss is always trying to convince me that this is a coincidence, but I don't trust in coincidence. I think it must be some kind of holistic connection between these facts. Anyway, Darwin was such an important scholar, and I think you really need to read something from Darwin to fully understand and appreciate how big, how towering figure he was among scholars. When I was a student, when I was a kid, I was taught about evolution. They told me that basically a bunch of morons tried to do some things before Darwin, and after Darwin, everything had already been said. Well, this is definitely not the case. There have been a lot of interesting and important scientists before Darwin and after Darwin. Now, these are just a few pictures from the internet of someone I knew the word of, but it's not a complete list. And I hope you also recognize the background, but it also has some importance. However, 1 hour is definitely not enough to talk about biological evolution. And if you are interested, I suggest you to read The Structure of Evolutionary Theory by Stephen Jay Gould. This is an extremely clear, nice, and compact book. It's only 1,500 pages, and really, the only problem is that it's not so recent because it has been written in 2000, and so a lot of interesting things that happened in recently, like epigenetics and so on, are not included here. But this is really a very nice introduction. However, let's talk a little bit more about Darwin. Well, as a computer scientist, biology and quantum physics are all things that I really don't very familiar with, and so a lot of people took from the idea of Darwin something, and they use something from Darwin. Well, if not completely, at least almost completely incorrect, but they have been inspired by some idea in the Darwinian theory. So first, we should not underestimate the effect of the accumulation of small variations. And this is impressive. So if you go piling up very small variation, you can really go a long way. And there is a book talking about it, and the metaphor is climbing Mount Improbable. But really, we should not underestimate the effect of small variation. Another important thing is that we may oversimplify the Darwinian theory as a sequence of two different types of steps. One step is mostly random, and one step is mostly deterministic. And so you have this alternating of two different steps, one random and one deterministic, and the overall behavior is again impressive. In evolution, we do not need to design changes. We just need to evaluate changes, and this is the most important thing. So we can have some new material, random material in the random step, and then we need to evaluate what just appeared in the random step. So just to make it clear again, evolution is not a random process. Although using Darwin's word, random variability afford materials. So it's a process that uses randomness, but it is not by itself a random process. So, well, from biology to computer science, again, well, evolution is not an optimization process. Real evolution is not an optimization process. All living creatures try to adapt to the environment. They are not trying to optimize something. Evolution does not have a goal, not at all. And evolution does not favor strength. But think of a mighty Tyrannosaurus Rex. Well, just temperature went down a couple of degrees and extinct. While the jellyfish is heavily flowing in water ever since. So definitely being strong is not very useful. And evolution does not favor intelligence as well. There are far more bacteria than scientists in the world. So, however, when all variations are accumulated in just one precise direction, the final outcome may look like the product of an intelligent design. And this is what we are interested in. So in nature, we have wonderful examples of this, like the leg of a bird. This is a great design. Or the eye of the octopus. This is another great design. Well, unfortunately for us, the eye of human are not really a good design. It's kind of an incompetent one, but it's at least the octopus eye is wonderful. So the starting point of my talk is how we try to pile up small changes in one specific direction, trying to build something and optimize something without the need of design. And this is evolutionary algorithm. So I will try to sketch what are the classical paradigms, just to have a common terminology, and then how evolutionary algorithm works, and how they do not work. And finally, just spend a few words about what we can call evolutionary machine learning. So, an evolutionary algorithm is a generic population-based meta-heuristic optimization algorithm that uses some mechanisms vaguely inspired by biological evolution. The first research dates back to the 50s. The first working prototypes appeared in the 60s. And we started having some really interesting research back in the 80s. Because evolutionary computation, well, we need to compute something. So we need computational power in order to do really something. And it's, let's say that we have real exploitation of this technology since the 90s. Now, some years ago, I've been asked to write a kind of review paper on the use of evolutionary algorithm in computer-aided design. And so I had to go through the three major conferences, Dark Date and ITC in our field, trying to find reference to evolutionary computation. Well, let me see, but it was not so easy because most of the people use evolutionary computation, but does not feel the need to acknowledge it in the title or even in the abstract? Well, basically because if you have a clever idea and you build something very nice, you want to describe what you build, there is no need to say that you used a hammer. And evolutionary computation is like a hammer, it's just a tool. So it can be used without the need to enter in detail. Although we have some more reference in around 2000. How can we use evolutionary algorithm in our problem, in our tool? Well, first of all, we need to take a possible solution, a candidate solution for our problem, and encode it in something we call an individual. Then a group of individuals is something we used to call a population, and then we need to measure how good is an individual, how good an individual is. As I told you, we don't need to design individuals, but we need to evaluate individuals. And this is done through a mechanism that is called, that is usually called fitness function. The reason is that the theory of Darwin has been explained as the survival of the fittest by Spencer. Well, we have reason to believe that Darwin never used the word by himself, but was pretty happy about it. And how fit is an individual means how an individual is good, is able to solve the problem in our case. And then we just need to implement the idea of evolution through a series of steps. And these steps are called generation in evolutionary algorithm. So, start again. An individual. We have a problem, we need to encode a possible solution, and this is an individual. So how we encode it? Well, whatever. Choose your favorite way. And an individual may be a list of real number, a sequence of cities if you're trying to solve a TSP, or a bit string, or a path if we are trying to run out of a maze and avoid a terrible monster, or a circuit, or a multigraph. So you can really do whatever you want. You just need to be able to encode a solution into some fixed form. And then you get some individual, and you put all these individuals in a can, and you have a population. And then evolution starts. How it starts? It's a sequence of discrete steps called generation. First, we need to select some individual out of the population. And this is called parent selection. Well, it's widely agreed that the fitness is in some way related with the ability of an individual to create offspring, to propagate in the subsequent generation. And so the parent selection is usually random, but this random is biased using the fitness, using the how good a candidate solution is. Now, this bias is also called sometimes we need to extract some parent out of the population. Then we take the parents and we apply what is called genetic operators. Well, genetic operators works at the level of the internal representation. They are called genetic operators because they are based on our encoding of the solution. So they do not work in the problem space. They are working in the solution space. We are just moving bits or integer or whatever. And using these genetic operators, some new individuals are created, and these new individuals are just sent back to the population. And these new individuals are called offspring. And then we need to evaluate the population. Well, usually evaluating the offspring, the new individuals, is enough. In some circumstances, we need to evaluate again the whole population because maybe something changed, but nevertheless, we need to do some evaluation. And at this point, we do a second type of selection, but is called survival selection. So we select some individual for the next generation. Well, usually survival selection is far more deterministic than parent selection, but different schemes may be applied. sometimes individuals also age, and so all the individuals are removed regardless of their fitness or other mechanism. And then we can simply keep on doing again this simple step. And that's all. That's all about evolutionary, what is an evolutionary algorithm. So it's incredible how simple it is, this stuff. And we can ask why. What are the classical paradigms that are used this idea? So doing a little bit of history, well, the first classical paradigm is probably genetic algorithm. They have been designed by Holland. It is very hard to understand exactly when Holland started to work on genetic algorithm, because a lot of his students started publishing papers related to the topic, but I even tried to ask him the exact date when he started, but it didn't reply. So we don't know when Holland started working. But in late 60s, early 70s, we have another two guys, very important guy, who started working and create another start for evolutionary computation. We have Reichenberg and Schläfer, and they started from a completely different approach. While Holland was studying, in some way, toy problem, and but he was interested in how in studying the adaptation of in artificial system, and then he has a very complex mechanism, but a very simple problem. These two guys took the exactly opposite approach. They have some practical problem, and they wanted to solve the practical problem. They wanted to design like a pipe, a nozzle, a wing, but they needed help from evolution, because they are not able to design it from scratch, but only to evaluate the effect of a possible design. And the third technique has been called evolution strategies. Then we have another third approach, again started in the same period of time by Fogel, and he arrived to the same idea of what I showed in one of the first slides. So the idea that we have a sequence of two contribution and the effective layering up of small variation, etc. But he started working on the idea of what is intelligence. And maybe intelligence means the ability to predict change in the environment, and then started thinking about it. And last but not least, also need to be listed in the classical paradigm. We have John Kosa, although it's definitely later approach, it's back in the 90s. And John Kosa initially tried to do a kind of a general framework for all evolutionary computation, but actually ended up in creating a completely new paradigm, but it's genetic programming. And these are the, let's say, the main kind of great old ones in evolutionary computation. But we have any number of newer approach, like all the swarm-based approach, swarm intelligence, where the goal is to try to evolve a set of simple agents and getting some emerging behavior, like a very effective way to explore the search space. And so we have a plethora of algorithms that use any type of animal, ants, bees, wasps, and so on, for solving problems. And another possibility is to remove the population from evolutionary algorithms. So instead of having an explicit population, we can have just store the statistical parameter of a population, and that leads to the so-called estimation of distribution. And just talking about real value optimization, we have differential evolution, that is a very effective way for exploring the search space. And a method that starts from evolution strategies, but is covariance matrix adaptation, but I guess it's right now something almost independent, and it's again an incredible tool for out-of-the-box optimizing a real value function. And I'm not talking about using evolution to study to study the behavior of a system. This is usually called artificial life, and this is something I'm not talking about and will probably deserve an additional hour. So why this very simple idea that has been discovered by different people almost at the same time and completely independently, why it works and how it failed, usually, well, most of the way. Well, we need to start with a very simple local search algorithm, that is hill climbing. So evolutionary computation can be seen as a local search algorithm. In a local search algorithm, you are just, you sit in a point of a search space, and then you explore just a few points around the point where you are, the current solution. And compared, hill climbing is just the typical example of local search. Now, compared to hill climbing, in an evolutionary algorithm, the concept of neighborhood is not so clearly defined. Usually because we have some technique, some operators that allow us to go from any point in the search space to any other point in the search space. However, small steps are far more probable than big steps. So we can think of a random mutation hill climbing, where doing a very small step is the most common things, but sometimes also larger steps are possible. Then evolutionary algorithms are population-based, and it means that they just explore several points in the search space. But again, this looks like a multi-start hill climbing. However, evolutionary algorithm has the powerful idea of inheritance. So I'm able to create a solution starting from two parents, and this new solution inherits some trait of one parent and some other trait from the other parent. And using this crossover, using this possibility, we have a really effective way of exploring the search space. Well, in natural evolution, we usually have three different concepts: fitness, genotype, and phenotype, and we almost all agree about that. So fitness, well, if we go into detail, people start to disagree, but let's say fitness is strongly related with the ability of an individual to create copies of itself in the subsequent generation. And we have the genotype, that is, well, DNA, etc., and the phenotype, that is the expression of a genotype in the actual manifestation of it. Well, in evolutionary computation, things are slightly more complex. Well, the fitness is usually how well the candidate solution performs in solving the task. And this is the easiest part. Well, it's not the easiest part, but it's easy. The genotype is how I internally represent my individual, and again, this is easy. The phenotype is slightly more problematic. So let's say that if I need to turn the genotype into something in order to check my solution, this something is the phenotype. So sometimes I need to transform the phenotype, the genotype, in order to evaluate it, and then this thing is the phenotype. Sometimes I don't need it. And in this case, genotype and phenotype coincide. So, for instance, the most common and probably most useless problem in evolutionary computation is the 1 max. In the 1 max, so what I'm trying to do is just to fill with 1 a bit string. And the fitness is simply the number of ones. So in this case, genotype and phenotype are exactly the same. And the fitness is just the sum of 1 at the end. Slightly more complex can be if I'm trying to evolve a function, a mathematical function. So I can represent in some way the function internally, like with a tree, and so this is the genotype. And then the phenotype. Well, let's say that the phenotype is the mathematical definition of a function. Or, if you prefer, it's almost the same thing. You can say that it is the plot of a function. It means that I can change the genotype. For instance, plus 40 plus 2, and getting 42 here in the phenotype. But instead of having 40 plus 2, I can have 41 plus 1 or 43 minus 1. And the result would be exactly the same function, because all this function would have exactly the same plot. And what is the fitness? Well, it depends on what I'm trying to do. Maybe it's the difference between the function I just created and the things I'm trying to model. And this level just show you how I have this kind of mapping between the different levels. So I can have different genotypes corresponding to the same phenotypes, or I can have different phenotypes corresponding to exactly the same fitness level. And this is going to create us a lot of problems, because basically what we can see is the fitness at the end, and where we can operate is at the level of genotype. So the more indirect this mapping is, the more problematic is to solve the problem. So mapping is fundamental. And this has been discovered basically in all possible paradigms in evolutionary computation, giving it to it different names, like strong causality, etc. But one term that is used very often is the locality principle. The locality principle means that if I'm able to map the things in order to be able to do a small change in the genotype, and this small change in the genotype corresponds to a small change in the fitness, well, a small change in the phenotype, and then a small change in the phenotype corresponds to a small change in the fitness, the locality principle is true, and the problem is easy. If changing something, a small change in the genotype, corresponds to a dramatic change in the phenotype and to a completely different fitness, then I'm in real trouble, because I'm not able to usually evolution is not working. Another important thing is that whenever I decide to encode my solution, I need to make sure that genotypic operators make sense. Genetic operator makes sense at the phenotypic level. So I can encode my picture as a string of bit, because we know that a picture or a movie is a string of bit. But then changing a bit makes no sense. Or I can, for instance, encode the story of my book as a set of different themes. And then if I have a set of different themes, I may even be able to cross over Jane Austen and George Romero and arrive with something like Pride and Prejudice and Zombies. Well, I have no evidence that the movie has been created using an evolutionary algorithm, but it looks like. And another very important thing is that we need to be able to evaluate individuals. So different individuals need to have a different chance of survival, because if all individuals have the same fitness, then the algorithm is not able to discriminate what is going on, and so we don't have any kind of evolution. And each single difference must bring an advantage. Because again, this is the idea of climbing mountain probable. So I need a fitness that in some way helps me walking toward the correct goal. Having different evaluation and having different evaluation in the correct direction. And let me stress that the fitness is essential. And this is a wonderful strip from BC, where the triangular wheel is an improvement over the square wheel because it removes one bump. And so if a goal is removing bump, well, it is an improvement, and your algorithm is going nowhere. So you need really to be able to reflect your true goal with a fitness function. And designing a fitness function is one of the main problems if you are using an evolutionary algorithm. But let's say say that we are able to design everything nicely. And how the evolutionary algorithm works? Well, we can say that we have basically two different phases in an evolutionary algorithm. We have exploration and exploitation. But we have exploration where the algorithm is trying to sample different points in the search space. And we have exploitation where when the algorithm is trying to improve locally, just doing small changes. Now there are two big families of genetic operator. One is called crossover. Crossover typically took two different individuals and then create an offspring that gets some information from both parents. And this is usually correspond to a big jump in the search space. Or we can have other kind of operation or operator like mutation. Mutation usually performs a very small change in the genome of an individual. Now, if the locality principle is true, changing slightly the genome, corresponding changing slightly the phenotype, but corresponding changing slightly the fitness, and I'm able to work and to slightly optimize my solution. However, there is one problem. Let's say that for some reason in my population all individuals are very similar. So if all individuals are very similar, then crossover stops working, because mixing two identical individuals is like doing nothing. So the ability to explore new solutions is definitely impaired. And this is one of the biggest problems in evolutionary computation. And let's say conventional wisdom suggests that increasing diversity should be beneficial. Well, however, we may stop a little bit and try to think, what does it mean that two individuals are similar? I'm talking about genomes, phenotypes, genotypes, fitness, and what does it mean to increase diversity? Now, this is a huge area of research in evolutionary algorithms, and well, this is interesting because in the original theory of Darwin, the divergence of character was one of the cornerstone. So individuals are progressively more and more different, and they are more different from the parents and inside inside the same kin and so on. And the reason is extremely simple. As Meyer put it, is simplicity itself. It is far more convenient to be different. If I'm different from you, I can eat something that you are not interested in, and my chance of survival are increased. So, definitely in nature, we have this incredible push, divergence of character, and push for diversity. And this is exactly what is not happening in evolutionary computation. So, let's say that the biggest single problem in evolutionary computation, once you solve all the encoding, mapping, locality, etc., the biggest single problem is sometimes called premature convergence. Well, premature convergence is actually an oxymoron, because what we are saying is that the algorithm converged into some point it was not supposed to converge in the first place. But the reason is that the population, all the population are, all individuals in the population are incredibly similar. And it can be expressed in several different ways. Even Holland, in one of his seminal works, talked about a possible lack of speciation, meaning exactly this. So that individuals are similar, more and more similar, and they are completely lack the ability of differentiating and creating something. Well, it is our belief that this is an endemic problem of evolutionary algorithm, and the reason is that we don't have an environment. So actually, we have a fitness function, but just kind of a proxy of the environment, and this proxy just is returning as one single aspect of the environment. And so the whole thing is built in order not to have an environment, and this is also why we talk about fitness landscape and not environment. And so the premature convergence is an endemic problem. And there is a lot of interesting research, but, well, no conclusive works at all, but a lot of interesting research where people try to alleviate or at least slow down a little bit this terrible problem. And, well, so almost everything about evolutionary computation. And, well, I have a few slides on evolutionary machine learning. Well, there is basically one reason, but it's not possible nowadays to talk about computer science without citing machine learning somewhere. So I felt the need to add this last final point. So let's say about machine learning. We all know this is this great windfall of machine learning. It just passed the peak in the Gardner hype cycle, and this is my belief. But machine learning is not completely a new field, but rather a new label, or more exactly, a label created in 1959 by Arthur Samuel. And but what we have is just a lot of good old math. Some very important advances. There are some key theoretical new things, and although unfortunately these are not the things that you usually see on the popular media, but we have some really impressive new results. We have new technology, and the result is that we have a bunch of really impressive results. We are able to solve problems that are completely unsolvable just a handful of years. So we're talking about learning, and there is an obvious connection using Turing word between learning process and evolution. And well, this idea of the alternating of two steps, one random, one deterministic, and then the selection of good things, and then inheritance and so on, can be applied to the process of learning. And it has been applied to the process of learning. It has even been applied to the process of cosmology. But back in the 50s, Alan Turing suggests that we can create this model of evolution. And this paper is usually also considered the starting point of evolutionary computation. And it cannot be a coincidence that a lot of seminal work in evolutionary algorithm has machine learning in the title, like Goldberg, Holland, genetic algorithms, and machine learning. In machine learning, because even the journal is called machine learning. So, what is evolutionary machine learning? Well, we can say it's a truism, but it's completely useless, perfectly useless option. Or, well, we had some evolutionary algorithm used to enhance machine learning. Starting from the 90s, we have some idea in trying to use classical evolutionary algorithm, for instance, for evolved neural network topologies. Or more recently, we can have evolutionary algorithm for doing some kind of smart feature selection. And obviously, they are incredibly slow compared to other machine learning approaches. But sometimes we don't have such a big data. We just talk about small data, and wasting time trying to select feature can be a good idea. Or well, recently I've been working on concept identification using evolutionary algorithm. I don't know if it makes sense, but at least it works. Or well, we have starting 20 years ago or so, some machine learning techniques used to optimize evolutionary algorithm parameters. So having an evolutionary algorithm at the same time machine learning algorithm, but just try to tweak it. And well, more recently, we started having some framework where maybe we used evolutionary algorithm for solving typical machine learning tasks, or just doing choosing the model using an evolutionary algorithm and then using a neural network or something else to do the fitting. So I'm seeing kind of increasing number of approach where the two things are in some way used together. And well, that's basically all. This is a classifier based on an artificial immune system, and it looks like okay, and a nearest neighbor in some way, but the points of the classifier are evolved using a typical the idea of the artificial immune system. So let's conclude my talk. Thank you very much. Do you have any question, comment?
Applications
of this? Oh no, it is slower. Well, the performance are good, even compared head-to-head to supervector machine. But application I cannot see. I think it's, if you need to classify, just use supervector machine. Yeah.
Can you give an example of a problem which cannot be solved by evolutionary algorithms?
Okay, a problem that cannot be solved by evolutionary computation. We have been trying to propose a workshop titled Evo-Don't, just showing a list of failures of evolutionary computation, but we failed, obviously, and no one accepted it in the evolutionary computation conference. I would say that whenever you have a solution, a possible algorithm, a heuristic that is working, that is completely useless to try an evolutionary algorithm. So you should only use evolutionary algorithm if you don't have any other option. So it's hard to say, but you compare with something. If you compare, usually you lose. But evolutionary algorithms really there are really a lot of cases where you don't know what to do, and throwing dices with some method, as in evolutionary algorithm, can bring you better results than throwing dices in general. Yeah.
Have you tried clustering? So instead of doing classification, considering something which is more approximate, like clustering, and try to figure out if it can give a solution to a problem which is not so well defined, like evolution?
Not yet. We didn't try clustering yet. No. But we may.
Because
yes.
Since it's a sort of a random exploration of the search space, well, it's slow to converge, but maybe it converges to a good solution.
Yes.
Which for clustering is still a problem.
Okay.
Differently from other domains.
Okay. So we can have a look at clustering. Thanks.
Giovanni, two comments and questions. The first one, so evolutionary algorithm belongs to, let's say, a larger family of meta-heuristics methods. Okay, and I would like to know your viewpoint concerning the possibility and the utility to try to combine together, let's say, more than one meta-heuristics in a sort of hybridization, say, approach. This is the first question. The second one refers to the last part of your talk, which is very interesting, concerning the relationships between machine learning and evolutionary algorithms. And my question is, do you think that these possible interrelationships could be available also for other meta heuristics like taboo search or simulated annealing or whatever?
Okay, so regarding the first question, just hybridization of evolutionary algorithm with other meta heuristic, yes, absolutely. And sometimes these techniques fall under the name of mimetic algorithm, although not everyone is agree on the terminology, but definitely I really think my sensation is that all these lines are blurry, and we are really going to some techniques that merge and mix all together whatever mean we have to try to solve a problem. So yes, it has been done, and in my opinion it will be done much more in the future. And talking about machine learning, I have a similar idea. I think that well, I don't like, but this is just a personal opinion. I don't like how the term machine learning is used nowadays, because it looks like an even growing umbrella, but just cover everything, and so that will obviously mean that all meta-heuristic techniques will be machine learning sooner or later. But even if we try to have a much more selective use of the term machine learning, yeah, I think that yeah, it could probably be, and but we are going to hybridize existing algorithms. I'm definitely not an expert of this thing, but my sensation is that we have a certain number of problems where we really need to be able to crunch an incredible amount of data. And but in most of the problems I am working with, we have a really small amount of data because they are maybe taken from a real biological sample or DNA sequencing, and it costs you every single line in your data set as a cost. And so if you are able to put some tricks, intelligence, whatever you are able to call it, to help the classical machine learning approach, you can improve and get better results.
I have a question about multi-objective optimization. Is that, in your view, is it really different from optimizing a single objective, or are there fundamental differences when you try to optimize more than one objective, more than one competing objective? Okay,
well, multi-objective optimization is definitely a hot topic, and people working in multi-objective optimization has some special terminology. For instance, multi-objective optimization is just a handful or maybe two of objectives, but if you have more, it's not multi-objective, it's many objectives. And we have all this strange lingo. And it's kind of a slightly different scenario, basically because in multi-objective optimization, as far as my personal experience, you can actually use the fitness as a reasonable proxy on the phenotype of the phenotype, because it's really unlikely that two different phenotypes will provide two different fitness on several diverse goals, and so you don't have usually you don't have any problem with premature convergence, and you don't have problem with keeping diversity in the population. However, you have a different set of kind of problems. Like you don't want your all your solution to be very similar. You want to explore the Pareto front in a reasonable way, and there exists some very good and effective multi-objective evolutionary algorithm like NSGA. is a typical example. But I know, I'm aware there is still a lot of research on that, and I'm also aware that there is some research that is trying to squeeze a multi-objective evolutionary algorithm into a single objective in a kind of pseudo-random way. So just try to find an aggregate fitness that works better than the typical aggregate fitness because it has some randomness inside. And so you are quickly able to find something that looks like a compromise, although it is not a full Pareto. But yes, so let's say the very basic things are the same, but as soon as you enter in detail, there is a different set of problems that you need to face and solve for multi-objective. Also, highly dimensional space are completely at least I don't have the mind power to understand a space, highly dimensional space. I mean, having all these points that are included with every points are just at the same distance, and the Pareto front is a nightmare because every solution is not dominated if you have enough number of solutions. So yeah, it's tricky. It's complicated, let's say. Do you have any other question? So, thank you very much. And,